Yeah, so welcome everyone to the second gravitational scattering seminar. We're pleased to have Professor Hikaru Kawai from National Taiwan University, and he'll be speaking to us about black holes as a state of ordinary quantum field theory.
Yeah. Okay, yeah, thank you very much for your kind invitation to this seminar. And my talk today is based on collaborations with Yukio Kokura, Peimin Ho, and Henry Liao. And we have been working on a self-consistent description of black hole evaporation. And actually, we have written several papers, and we started this direction 9 years ago. And I would like to summarize them today. So the basic idea is the following. We start with the fact that black hole is to evaporate. So first we consider a spherically symmetric evaporating black hole and see what happens if we add a particle or a thin shell. Then if we see the evaporating black hole from the outside, the metric looks like this. So this is a Schwarzschild metric, but AT is proportional to GMT, and AT is a function of T. And because of Hawking radiation, AT shrinks to 0 as this equation, d dTA is minus some constant 2c divided by AT squared. Okay, this comes from Boltzmann law. The temperature is proportional to 1 over A, and 1 over A to the fourth multiplied by area. So this is 1 over AT squared. So from this, we see the black hole evaporates in the time scale of A cubed. So if A is large, or the lifetime of black hole is really large. So this is A. So this finally evaporates following this rule. And we consider a motion of a particle or a thin shell added to this black hole from outside. And as we will discuss, the particle will never go across the horizon. So this is not the horizon in the real sense, but we simply call A as horizon. So, and as we will see, the particle will never go across the horizon, but the black hole disappears before the particle reaches the horizon. So more precisely, when the particle gets close to the horizon AT, it becomes ultra-relativistic, and the position R is determined by setting ds squared equal to 0. So by setting ds squared to 0, we have dr dt is this quantity. So we have dr dt is minus RT minus AT divided by RT. So we want to see this RT really behaves like this. So RP is always outside of A. So this is what we want to show. So in terms of delta R is RT minus AT. So this is a deviation from the horizon. So if we take a time derivative of this, dr dt is given by this, but the numerator is delta t by definition. So dr dt is given by this, and we have minus A, so we have minus dA dt. But if dr is smaller than R, so this means if the shell is close to the horizon, we can replace RT to AT. So this equation can be approximated by this equation. So this is just a linear equation for delta R with inhomogeneous term. So we can simply solve this by the ordinary technique. So delta R can be written like this. So this is a general solution to the homogeneous equation, this one equals this one. So we have some constant multiplied by 1 over AT and integral and exponential. And this one is a special solution to this inhomogeneous equation. So we can easily see that if we take time derivative of this one, so if time derivative hits here, we have minus dA dt and this one. So this is this gives this one 1 over d. And if we hit the time here, we have 1 over a here. So sorry. This one reproduce this time. And if dt hit here, and so t is t prime, so this is become 1. So this is equal to this. So we can easily check. This is a general solution to this equation. So because AT and dA dt can be considered to be constant in the time scale of A, because as we have discussed, the AT becomes to 0 in the time scale of A cubed. So in the time scale of A, the time scale of A is a time scale for RT gets close to AT. So this is a time scale for delta T. So if AT and dA dt changes slowly compared with delta R, we can replace AT here and here by some constant AT. So the second term can be approximated like this. We have minus dA dt, but since dA dt changes slowly, we just approximate this part by dA dt at t. So we plug this out here. And we have this integral dt prime from t0 to t. And here again, we approximate AT double prime is almost constant. So we plug this out here. So we have t minus t prime divided by AT. So under this condition, we can approximate the second term by this. And now we can easily integrate over t prime because this is, we assume this is just a constant. So the t prime integration is just exponential. So we have inverse of 1 over a. So we have a and 1 minus this quantity at t equal t t0, t and t0. So we have this expression. So therefore we have this formula. Delta t is approximately equal to something like this, C0 exponential minus from T0 to T. And also this is the second term we evaluated. So if T minus T0 is greater than A, so as we have seen, the delta T, the typical time scale of delta is A. So for long time, T minus T0 is greater than A, but they should be less than A cubed. So for long time compared with A, we can drop this because this exponentially down. So we can drop this term and this term. So we see delta R is approximated by this quantity. So, but delta R is R minus A. So R is approximated by A plus this constant, minus dA dt and AT. So we call this combination R, capital R AT. And so once we know AT, then and also we assume that because of Hawking radiation, dA dt is minus 2c over AT squared. So by plugging this, we have R, capital R is given by A plus this number, because dA dt is minus is plus. So heuristically, we can easily understand the situation is the following. So we have a time and R, and we have a slowly shrinking AT here, and R is approaching to A exponentially in the time scale of AT. So when RT gets close to AT in time scale of A, but because AT shrinks, so AT shrinks by this quantity, minus this one, minus A times dA dt. But the dA dt is given by this one. So this is multiplied by minus A, we have 2c over A. So this is a 2c over A here. So I think it's easy to understand what is going on. So AT is shrinking to 0, but R is coming close to A. But the distance between R and A is about 2c over A. So this means the shell or particle can never go across the horizon. So if we see in time scale AQ, so A becomes 0 in time scale AQ, but the particle will never go across to A. So this is why we can say the particle will never go across the horizon, but the black hole disappears before the particle reaches the horizon. So after the shell put outside the core black hole approaches to R, capital R, in a time scale of A, the total system looks like a black hole with mass m plus delta m, where delta m is the mass of the added shell. Now the radiation of the total system consists of two parts. Okay, one is from the inside black hole with a slight redshift due to the outer shell, and the other is the radiation created by the outer shell itself, these red arrows. Then the total system looks like a black hole with mass m plus delta n. So applying this argument recursively, we conclude that any object we recognize as a black hole actually consists of many shells. And if we see the system from outside, it looks like an evaporating black hole of the ordinary picture. But it has a well-defined internal structure in the whole region. So this is a basic picture. So in order to prove the above picture, we have to solve the coupled system of matter and gravity. But if we want to consider full quantum mechanics, it's a really hard problem. We have to quantize gravity and field. But as a first step, we can try to solve the self-consistent Einstein equation. So G mu nu is the Einstein tensor equal to h pi g and expectation value of T mu nu. So here the metric G mu nu is regarded as a classical field and determined by the Einstein equation from the expectation value of the energy momentum tensor T mu nu. And the radiation fields are treated quantum mechanically on the background metric G mu nu. So actually, once G mu nu is given, the time evolution of the fields are determined from a proper boundary condition. And also we can calculate the absolute, the expectation value of T mu nu. So here so in this sense, we call this semi-classical approximation. So we treat the radiation fields quantum mechanically, but we treat G mu nu as classical field. So in the following, we first construct a candidate metric G mu nu that describes the inside and outside of the evaporating black hole. And we then check that the self-consistent equation is indeed satisfied for this metric by evaluating the expectation value of T mu nu. And in particular, we'll see that T mu nu is determined by the 4D Weyl anomaly plus some assumptions if we consider conformal field as a matter field. So this is a strategy. So let's construct the candidate metric G mu nu. So first we consider a spherically symmetric collapsing null shell. So here RSU is the radius of the null shell. So we have a null shell. And this is collapsing to Z. And the metric inside the shell is flat. Okay? We are considering a thin shell. So the metric inside should be flat. So the metric inside can be written using right-to-right coordinate capital U. And this is just a flat Minkowski space. ds square is minus du square minus 2 du dr plus r squared d omega squared. So this part is just flat. And we assume that the energy emitted from the shell simply flows to infinity, like this. So then the metric outside the shell is the outgoing Bayesian metric. So the metric outside the thin shell can be written like this. ds square is minus 1 minus au divided by r du square minus t du dr plus r squared d omega squared. But here small u is a right-to-right coordinate outside the shell. So capital U is a right-to-right coordinate inside the shell, and small u is a right-to-right coordinate outside the shell. So in terms of the Penrose diagram, our geometry is the following. So since A disappears to 0, so essentially the global structure is the same as the Minkowski space. So and shell, the radius of shell becomes 0 again. So this is the trajectory of the shell. And here we consider the null, massless, so null shell. So this is a straight line here. And inside of the shell is flat space, and outside is Bayesian metric. So and we have outgoing radiation corresponding to the Bayesian metric. So this is a geometry of one null thin shell. And the junction condition of capital U and small u is given by the fact that Rs is the locus of ingoing light for the metric of the both sides. So this means, so if we see this shell from inside, okay, this is a null shell. So the motion is given by setting this part equal to 0. So we have dr equal minus 2dr equal du. So this one, minus 2dr is du. And also if we see this shell from outside, again, this is a null shell. So by setting this equal to 0, we have minus 2dr equal 1 minus a over r multiplied by du. So we have this equation, this equal to this. So we have two equations for these quantities. So once AU is given, this equation determines, by solving the first equation, this equation gives RSU. RS is the position of the thin shell as a function of U. And also by equating this one, after now we know AU and RSU, so this gives a ratio between D capital U and D small u. So the relation between capital U and R small u is obtained. So next we consider multi-shell, and we eventually want to consider continuum distribution. But before going to continuum distribution, we consider many number of shells. So here we consider n shells, and I is a label of ice shell. Okay, so the position of ice shell is Ri, and the right-to-right coordinate outside the ice shell is Ui. So again, and also Ai is equal to 2g mi, and mi is ADM mass inside ice shell. So including this Ri ice shell itself. So if you see the system outside of ice shell, the total ADM mass is mi, and the corresponding Schwarzschild radius is called Ai. So we have A1, A2, and An, and for simplicity, we set A0 is 0 and U0 is U. So U is right coordinate at R equals 0. And formally, we set A0 equals 0. So mass is 0. So for
can I ask a question?
Yes.
Here the Mi is the mass of the one shell. The mass.
Oh, okay. Mass is the Mi is the total of this shell.
Okay. Yeah,
So,
it's inside the Mi the total mass of the shell inside the.
Yes.
I see.
Mi is the total mass. Yes.
Okay. Yeah. Thank you.
Yeah. Thank you very much. Yeah. So if we see the metric just outside the ice shell, the mass is the total mass is AI. So we have this Bayesian metric. So 1 minus AI over R and the UI square. UI is a right coordinate outside ice shell. So DUI square minus TDUI dr plus R square d omega square. And also if we consider the region between I and I minus 1 shell, so we have again this part is Bayesian, but the mass inside I minus 1 shell is AMI minus 1. The corresponding radius is AI minus 1. So we have this Bayesian metric in this region. So the junction condition is the same as before. So we see the motion of ice shell from both sides. So if we see this, they are null shell. So the motion of ice shell from outside is obtained by setting this one equal to 0. So we have sorry, I should put Ri. This is my metric, so this is okay. So ice shell is by setting R to Ri. So 2dRi is this quantity multiplied by dUi. So dUi Ri divided by Ri minus Ai. And also if we see the ice shell from inside by setting this part to 0 with R is Ri, we have this equation minus 2dRi equal this one with R replaced to Ri. So Ri divided by Ri minus Ai minus 1 and dUi minus 1. So from this, from the first equation, we get dRi dUi is minus Ri minus Ai divided by 2Ri. And also by comparing this one, we see the ratio between dUi and dUri minus 1 is equal to the ratio between this one and this one. So Ri is common. So we have Ri minus Ai minus 1 divided by Ar minus Ai. And we can derive this as 1 plus Ri minus Ai, and here Ai minus Ai minus 1. So we can just derive this in this way. The point is we are considering, eventually we are considering a continuum distribution. So Ai minus 1 is very small. And on the other hand, Ri minus Ai, as we have seen, the shell never reached the Schwarzschild radius. So this one is non-zero. Okay. So this is the point. So if we take the continuum limit, this one is small, but this one is not so small. So, and also we assume that each shell behaves like the ordinary evaporating black hole if we look at it from the outside. So this is a, sorry, I think I should put 2 here, but so this is the equation we use. So Ai dAi du is minus C 1 over Ai squared. And each shell has already come close to Ai. So as we have seen in the beginning of this talk, we have seen in the time scale of A, each shell comes close to A, but it is always apart from A by this quantity, 2C over Ai. So here we assume each shell has already come close to AR. So we simply said Ri is equal to AI plus 2C divided by AI. And then we consider this quantity, eta I is log of du dui. Here ui is the right coordinate of the ice shell, and the capital U is the right coordinate at r equals 0 at the origin. Okay, and taking log, and we call eta I. Then eta I can be evaluated as follows. So if we take the difference eta I minus 1, then by definition, this is log of du dui divided by du minus 1. So du cancel, and we have minus log du I minus 1 dui. But this ratio is given here. dui minus 1 is 1 plus ai minus 1 divided by ri minus ai. So this one is given like this. And as I said, this quantity is small in the continuum limit. So we can replace this to minus of this one, 1 plus small number, so this one. And because of this assumption, Ri minus AI, so deviation of the position of ice shell from the Schwarzschild radius is equal to 2C over AI. So we have this expression. And now we know AI and AI minus 1 is cross. So we multiply AI to numerator and denominator. And in the numerator, we have AI divided by 2, and we replace it to, AI to the average AI plus AI minus 1 divided by 2, because AI and AI minus 1 are very close. So we can replace AI to the average of AI and AI minus 1. And then the product of AI minus 1 and AI plus AI minus 1 is the difference of square. So we can approximate this to AI square minus AI minus 1 square if AI is close to AI minus 1. So, and also, so we have eta I minus eta I minus 1 is something like some constant AI square minus AI minus 1 square. So once we have some initial condition, so we have assumed A0 is 0. And also eta 0 is, so the U0 is U. So eta 0 is 0. So from this initial condition, we can solve this recursion equation. And actually, eta I is equal to 1 over minus 4i AI squared. So in this way, we can calculate eta I.
Can I ask a quick question?
Yes.
So in the previous slide, the eta I minus 1 and eta I are both evaluated with respect to du. And I mean d capital U, the flat spacetime capital U.
Oh, yes, yeah.
So is that a legitimate expectation? Like I would have expected eta I minus 1 to be related with like U with the subsequent layers, the subsequent shells, like the shells are stacked one on top of the other. So to what extent are we assuming that for eta I minus 1 also we can just write it as a du by dui minus 1? So that assumption.
Okay, so we are now considering multi-shells, right?
Yes.
And from this equation, we know the ratio between ui and ui minus 1.
Yes.
And what we are doing is to multiply these equations, we get dui divided by du.
Okay, you're saying if you take it as a continuous, if you take all of it into account.
Yeah.
Okay.
So we started from a discrete shell, but if we take a continuum limit, so
okay.
AI and AI minus I is AI minus 1 is very small.
Okay.
Yeah. So
this is the reverse.
very
Like
close
you're
to
saying, if AI minus 1 is small,
Yeah,
then
yes.
that assumption can be
Yeah,
taken.
that's right. Yeah, AI minus 1 is small in the continuum limit. And on the other hand, Ri minus AI is not small because of this.
Ah, okay.
Yeah.
That
So
is
this-
coming
yeah,
from the
yeah,
that
this
is
a very
coming from the
crucial point.
assumption that it is behaving like an ordinary evaporating black hole.
Yeah, right.
But that's an assumption.
Yeah. So this is a very crucial point. So the shell never goes cross shell never go across.
So there's no shell crossing which is taking
Yeah.
place in this multi-shell.
Yeah,
Okay.
shell is always apart from Schwarzschild radius by this amount.
Okay. Okay.
However, here I have a puzzle. So this combination AI plus 2C over AI, right?
Mhm.
So could it be possible Ri with in some sense, here you assume that Ri also sequentially ordered, right?
Mhm.
But this AI function of AI is some kind of the one increasing term plus the decreasing term. They the minima somewhere, right?
Mhm.
So could it be possible in some sense for some AI value, the I will not be sequentially ordered?
Oh yes, yeah, okay, yeah, something. Yeah, so here we assume AI is in sequential order.
Yeah.
And at least for this time evolution, they are always ordered in this way.
Okay. But I mean, if even AI assumed to be sequentially ordered, it's possible for I to be also sequentially ordered, or there's the possibility I would not be sequentially ordered, given AI is sequentially ordered.
Okay, if we solve this couple system, they will never cross.
Okay.
Yeah, if Ri is greater than Ri minus 1, so in any time, or it is all Ri is always greater than R minus 1.
I see. So this was solving. This was from the obtained from the solution.
Oh yes. Yeah.
Okay. Okay.
Yeah. So that these statements are true if we're taking null shells, right? So if we're assuming null shells, then we can have the situation where
so
it's a uniform distribution.
Yeah. So the point is, if the time, okay, so here, okay, we consider just null shell. But even if they are massive shell, in the very long time, or they will come close to ultra relativistic.
Okay.
So the motion of the shell can be described by setting this one equal to 0.
Here, there is a concern. Of course, this is out of context here, but usually, I think below the, I think there's the isco, right? Below the isco, then the inertia will not be stable. Yeah, so would be possibly this spherical symmetric picture will not be whole anymore. Maybe you have some quantum fluctuation. You will introduce an isotropy very quickly.
Yeah, okay, so here, okay, we just consider spherical symmetrical configuration.
Yeah.
And because of this spherical symmetry, when we are discussing the motion of, for example, this shell, we can forget about outside. This is what we have assumed.
Yeah, but if there is a small perturbation, maybe this signature will just, spherical signature will just destroy.
Yeah, so yeah, I want to see what happens if we give some non-spherical symmetric perturbation. But so yeah, I haven't succeeded. So
I see.
Yeah, so this is just a pure assumption. And
okay. Yeah, it's okay. I think I can understand. But even with spherical symmetric picture, give some hints. Yeah. Thank you. Yeah.
Thank you very much. Yeah, I think it's a really good problem to try to see spherical non-symmetric perturbation and see what happens to this solution. Thank you very much. So from this, we can determine the metric in the continuum limit. So the metric. So the metric at the spacetime point Ru is determined by considering the shell that passes the point. So suppose the ice shell passes the point Ru, and then the metric is given by this. This is the Bayesian metric. And as we have seen, 1 minus AI over R is Ri minus AI divided by Ri, but we assume this one is 2C over AI. So and the AI and the Ri are close, so we can approximate it by 2C over R squared. So in the continuum limit, this part can be approximated by 2C over R squared. And also from du di, this one is by definition exponential minus eta I, but we have seen eta I is minus 1 over C 4C AI squared. And AI is R, so this one in the continuum limit, this one is exponential 1 over 4C R squared. And in this way, we have the metric in the continuum limit. So ds square is du is using this. Du is expressed in terms of d capital U, and this one multiplied by du. So this one is square. So square of this, we have exponential minus 2C over R square and du square. And this factor becomes this. So this one can be written like this. And also this part, so dui du is this one. So exponential, we have this factor, exponential 1 over 4C R square and 2 and du dr. So in this way, we can determine the continuum, the metric in the continuum limit. So far we are considering collapsing the shells, but we can express this in terms of the time coordinate. So if you introduce a time coordinate by this expression, dt is du plus 2 R square over 2C and exponential minus 1 over 4C R square dr, we can see that the cross term disappeared and we have this metric. So ds square is minus 2C over R square and this factor, and dt square plus dr square.
So is this metric also the vacuum solution?
Yes, if we have nothing, this should be vacuum.
Okay. Yeah, but then they see. So in some sense, it is pressure or is mass.
Okay, but vacuum solution means outside.
Since you assume that the last things are going to the black hole, right?
Okay, yeah.
So
okay.
after that, I will assume that this metric would.
Yeah. Okay, this one is inside of shell. Okay, so the picture is thank you very much. It's a good point. So we are considering inside this object, and outside we have just vacuum solution, right? So what we are considering is inside.
Okay, so that's why the inside. So maybe that will have some. It's not vacuum solution. You have some affecting matter, right?
Yeah. So outside should be vacuum solution, right?
Yeah.
So now we are going to see the outside vacuum solution can be continuously connected to this inside solution. Mm-hmm. This is the next step we do.
Okay.
Yeah. Thank you very much. Yeah, it's a very good point. So this is the inside of our object. So and it is rather surprising that the inside metric is static, although each shell is shrinking. We started from this shrinking shell, but the inside metric is actually static, even like this. So now we are going to discuss the outside region. So before that, we want to consider surface of this system. And as we have seen, the outermost part of the matter approaches capital R in the time scale of A, and no matter how they are distributed initially. So this is a point. So no matter how the outmost particles are distributed, they eventually come close to capital R. So this means it is natural to expect that there is a sharp boundary at capital R. So outside of, if we see this outside, the outside is almost empty. And from the outside observer, the object looks like the same as the conventional black hole. So this part is conventional, almost vacuum solution. But so we have some surface at RT. R is, as we have seen, AT plus 2C divided by AT. So this is very close to the Schwarzschild radius. But the surface is a bit outside of the Schwarzschild radius. And the inside, the matters are stuffed inside the surface. So this is our picture. So I want to see how they are connected. So the candidate metric is constructed by connecting the Weiser metric outside to the internal metric we have seen. And so outside the surface, we have a Weiser metric. And inside the surface, we have this metric obtained from multi-shell model. So using small du is capital Du is a right coordinate at r equals 0. So I want to change this to this coordinate, d small u. Small u is a right coordinate at infinity. So we change our variable by this expression, and then this part is replaced by this. So du is replaced to du multiplied by exponential minus of this. So we have, so this part becomes exponential minus 1 over 2c capital R minus R squared, the minus of plus here. So, and same here. Again, from the conversion factor, we have this R square is replaced to capital R square minus R squared. So the point is, if we consider the surface at R equal capital R, then at R equal capital R, this one disappears, right? Because if small r is capital R, this one is 0. So this is connected to this smoothly. And also, as we have seen, if R is capital R, this one is equal to 2c over R squared. And this factor becomes 1. So again, this one is smoothly connected to this. So in this way, we can construct a candidate metric, including outside and inside. So, and also we can make a stationary metric, or we can construct stationary metric of a black hole in the heat bath of the Hawking temperature by connecting the Schwarzschild metric to the internal metric at the surface R. So we are now we are considering black hole put in a heat bath with Hawking temperature. So outside is almost Schwarzschild metric, and the inside is, as we have seen. So in this TR coordinate, as we have seen, this is a static metric. So inside the object, we can use this metric. So and also by changing the time to the time at infinity, we put this factor. Okay, this is just a constant. So this is a metric. And again, as we have seen, at R equal capital R, this one is replaced to this. So this is connected smoothly. And also this one is connected to this. And this one becomes 1. So again, we can make a metric of the entire region. So in this way, we can construct a candidate metric for our object. So outside is almost vacuum, and the inside is quite dense. So this is our solution. So the next step is to evaluate the expectation value of energy momentum tensor, and then see whether semi-classical Einstein equation is satisfied or not. So let's calculate the expectation value of energy momentum tensor in this background. So here I would like to make sure what assumptions we made. So we are considering a spherically symmetric collapsing matter and regard it as a collection of null shells. And we have assumed that because of the spherical symmetry, the time evolution of each shell is not affected by its exterior region. And each shell looks like the ordinary black hole when it is observed from outside. And in particular, the total radiation coming out of each shell is the same as the ordinary black hole. And also we assume the energy emitted from each shell simply flows to infinity without being reflected back. So this is the reason why we consider the Weiser metric. So in terms of the critical coordinate, capital U and capital V, this means, so the third assumption means that only the UU component of T mu nu is non-zero in the intershell region because we use Weiser metric. So Weiser metric has the non-zero component of Weiser metric energy momentum tensor is just TUU. So inside shell, we have just TU. On the other hand, along the collapsing null shell, we have non-trivial values for TBV because the shells are coming. So we have TBV. And furthermore, from the Barabes-Israel null condition, we have the surface pressure along the shell. So surface pressure is proportional to A dot. So we have a non-zero T theta theta and T phi phi. So therefore, after taking the continuum limit, the total energy momentum tensor has non-zero values except for UV component. In this way, the assumption 3 is equivalent to TUV itself. So for a while, we use this assumption, and we'll weaken this assumption later.
Sorry.
Yes.
So in this sense, all the matter, no matter what kind of equations you start with, you assume that near the horizon, everything becomes just some kind of photon-like matter, right?
Oh, yes.
But in some sense, this is not the traditional Israeli junction condition. The equation of motion, the equation of state will play some role to determine the motion of the shell, right?
Oh, yeah. So, yeah, yes. So we have a null shell here. And this is the Israel Barabes Israel condition for null shell.
Yeah.
And and this is a typical formula. The pressure along this shell is
yeah, but the point, if we have different equation of state, it also means that in your consideration, it will just become a null shell and it become a null-like matter in some sense. Yeah. I mean, in some sense, if this is the case, I can imagine some information hidden in the equation of state will get lost, right? When everything approaches to horizon and on the black hole. Of course, if it really a black hole, I think this kind of the information paradox. But if you don't form the black hole, it just stack outside the horizon. In some sense, it still have some matter, right? Yeah, I just wonder how the information will get lost when the matter.
Okay, so the point is, actually, we don't have a horizon. We use the term horizon, but they shrink to zero. so there is no horizon.
Uh-huh.
Okay, so this is the point of our picture.
And then do we have, as I say, the information may contain inside, for example, equation of state. It tells us what is the different matter, right? But in your consideration, it seems that everything just become a null share, and the equation of state seems universal from your consideration.
Okay, so
that's a little bit puzzle to me. How the information before it comes to the horizon, we get some information. We can tell the difference of the matter by equation of state. But once it approaches the horizon, it seems everything just information just lose.
Okay,
right?
suppose so this one. Okay, so let's go back to black hole plus one shell.
Okay.
Okay, and then the information carried by this shell comes back. Okay, so this will never go across the horizon. So information is just kept here.
Okay.
And it comes back when everything when inside this.
You mean when the horizon really shrink to zero, in some kind of evaporation of the black hole happen, then all the information will release through the thin shell again.
Yeah, I think so. Yes.
Okay.
Yeah. So this is a picture.
I see.
Yeah.
So since we're on this slide, can I ask a question which I have? So in the original, the first part of the talk, when we were describing T.
Which slide?
In the first part of the talk, like these slides only, right here, these slides. Yeah. So
this one?
Yeah. So T here is T as measured by an asymptotic observer in the space-time. Am I right? Like all of these are like in some kind of a static slicing of a presumably black hole space-time.
Okay, so this one is not exactly the black hole space-time, right? Because
a presumably black hole. That's why. But
okay, okay. If we assume A is constant, is it okay?
Sure, but like even A evolving with respect to T, this T is the time of an asymptotic observer. So what I mean to say is like this R, which we're talking about, is not an infalling observer.
Okay. So for this AR to 0, okay, this is just okay. So outside is just outgoing Vija, for example. Okay. So then there is no singularity at here.
Okay.
Okay. So this is not a matter of coordinate patch. Okay.
Okay. So this is a coordinate independent.
Our Penrose diagram is exactly this one.
Okay.
So this one becomes to 0. So this is outgoing Vija. So we don't have any singularity here.
Yeah, that's fair enough. But when I mean to say that RS as a function of T means RS is a function of T in terms of global coordinate time T. It's not RS as a function of its.
Okay, this U is a global coordinate in this case.
Right.
Okay, if A is constant, the U is not a global coordinate, right?
Right.
But because A becomes to 0, or U is a global coordinate.
Okay. And even this U is technically like the U of an asymptotic observer again, right? It's U from the perspective of null infinity. Is this correct? Like U is technically U measured from like an asymptotic observer.
Yeah, U is just a coordinate here.
Yeah. Okay.
Yeah.
Thanks.
So I think this is related to the usual folk law about a black hole, right? We usually are told that if you're choosing this kind of coordinate is for a simple observer. So everything just because the large redshift, everything just stacked outside the horizon. But you just consider free falling observer, then they are just directly past the horizon. So I think I also have the same question as Karen. So this, how do I understand this? This is quite different from the usual folk law taught by the textbook, right?
Yeah. So this is totally different. We do not have any horizon.
Okay, so you're saying that there is no picture of like black hole complementarity which is showing up here.
Yeah,
like
I will show why Hawking radiation appears even in this case.
Okay, so just
Okay.
to be a
So-
little
so,
clear.
maybe I should emphasize that our metric has no singularity, so no horizon. But still, if we calculate the energy momentum tensor, we have a Hawking radiation outside.
But Kawai-san, you
Hmm?
at the very beginning you using another coordinate with r. Then in that coordinate we actually have the singularity, right? In this coordinate we don't have singularity, even r equal to ai. But I remember it previously at the very beginning you using this Schwarzschild-like metric, right? And then they usually lay the coordinate singularity at ai, right? At a.
This one?
Yeah, yeah.
Yeah.
So in this coordinate, we actually have
But
singularity at
anyway,
a,
the
right?
point is A itself becomes to 0. Okay.
Right. So this is partly what I was getting worried about. So A becomes 0, and your claim is that R will never approach A. That's the statement.
Okay.
Right.
Okay.
But
I think rigorously speaking, I think it's better to go to Weiermet or Eddington-Finkelstein coordinate. Okay. So I think it is better to go to Eddington-Finkelstein coordinate.
Okay.
Okay. And in this case, if AU goes to 0 for large U, so the Penrose diagram is just look like this.
Yeah.
Okay, this is just an outgoing Weiermet.
Yeah, in this case, there is no coordinate singularity because it just go back to Minkowski space. Yeah.
Yes.
Yeah.
Yes.
I mean, we can only comment on coordinate singularities if you compute scalar invariant and check that it is convergent, if it is divergent.
So the method, the curvature is explicitly calculated for Weiermet metric, right? And we have no singularity here.
Right. So that, yes, that I'm agreeing. I'm just saying that it would follow from calculating like Kreshman scalar and then checking that it has no divergence.
Yeah.
Okay, thank you.
Okay.
So for the inside metric you just derived, do they have curvature singularity somewhere I equal to 0?
Yeah. So, thank you. Yeah, it's a very good question. Yes. Okay, so for this inside metric, sorry. Sorry, this one.
This one.
So for this inside metric, and at r equals 0, we have singularity.
I see. So it's indeed a black hole, right?
Yeah, but this one is very small. So if r is close to Planck length, so this one has singularity. So okay, yeah. So anyway, I will talk about that. But yeah, it's a good point. So we calculate the R and Kreshman and these things, and they are all proportional to 1 over C.
I see.
Yeah. So and C is the strength of Hawking radiation. So the interesting point is if we have a strong Hawking radiation, this is suppressed from if C is 1, for example, this is just a Planck length. But if C is large, this one is smaller than Planck length.
I see.
Yeah, so this means if we have a strong Hawking radiation, or we have a sufficiently large number of fields, and then we have a strong Hawking radiation. For example, for standard model, say it's about 100. So in this sense, if we have sufficiently large number of fields, these curvatures are smaller than Planck mass.
I see. So you have a natural cutoff
in
some sense.
Yeah.
Thanks. Yeah.
Yeah. So in this sense, the title of my talk is by a description of black hole by ordinary field theory. So in this sense, okay, I would say macroscopic black hole, if this means A is greater than Planck length, can be described by the ordinary field theory. And we do not need to consider string effect, except for the very small region, RLP, or the last moment of the evaporation. Yeah, thank you very much. This is a very, very good, crucial point.
Thank you. Yeah.
So now, so coming back to this problem, so we are trying to solve expectation value of T mu nu. But so for a while, we assume that TUV is 0. And then if we assume this from the conservation of energy momentum tensor, we can express T mu nu by T theta theta. So first we examine the consequence of the conservation of energy momentum tensor. So what we want is to calculate T mu nu for the background metric. This is our background metric. So here I use a static method, TR code. And this can be easily mapped to Kruskal coordinate. And exponential phi is just square root, just this factor, exponential phi. The conformal factor is just this factor. And dr du is just square root of ratio of this. So du dr is minus dvr, and this one is ratio square root. So we have c over r square exponential 1 over 4c r square. Then in this coordinate, the energy momentum conservation can be written in this way. So here T theta theta is, here we have R del UR and the exponential minus Y. And we have TUU, TUV, and TUV. And but we set TUV 0 for simplicity. So this means TUU can be evaluated from T theta theta by integrating over V. But since our metric is static, the integration is just over R. So, and also for this one, we have TVV here and TUV here. So from this, again, we can express TVV in terms of T theta theta. So in this way, if we set TUV equals 0, we can express all the energy momentum tensor by T theta theta. So more explicitly, we have TUU is given by the integral of T theta theta. We have this factor exponential phi and R, and dr, and dv is, since dur is equal to minus dvr, this part becomes R integral. So this means R squared TUU is T theta theta multiplied by exponential phi and R and integrate over R. So this is the expression. And also TVV can be expressed by the integral of T theta theta with this weight. And this one is just boundary value at theta R equals 0. And assuming that TU and TVV are not so singular, we simply set they are 0. And then, and also we assume T theta theta does not depend on R so strongly as exponential phi. As we have seen, exponential phi strongly depends on R, like exponential of R squared. So if we assume T theta theta changes not so strongly, so we can replace this integral by okay, so this part is, I just rewrite this by dropping this, and exponential phi is this. And I plug this one, I just multiply this one and divide it by this one. Okay, so this one just cancel. So then if I write in this way, at R equal, so this one is very small if R is much less than R prime. So because of this factor, this integral dominates at R prime around R because of this. So as we have assumed, this one changes slowly compared with this. So we can pull this out with R prime replaced to R. So this one is pulled out here and same here. So this part is replaced with this. And then we have integral over R, but this one is around R prime is R. we can do Taylor expansion and take the linear term is r minus r prime over c. So this one is just a integration of exponential. So we have c over r. So this one multiplied by c over r, we have this. So in this way, we have TUU and TVB are equal to this one divided by r squared. So we have this expression. So under this assumption, we can easily express TU and TVB in terms of T theta theta. Or in terms of local time, du equal exponential 1 over 4c r squared du. So this part is canceled. And we have this equation. TUU is equal to this one. So then the problem is reduced to evaluate T theta theta. And as we discuss now, T theta theta can be easily evaluated from the Weyl anomaly. So in four-dimensional Weyl anomaly. So to be concrete, we consider four-dimensional conformal field. Then the Weyl anomaly can be written like this. Energy momentum tensor is proportional to Weyl tensor square, and G is Gauss-Bonnet, and this is D'Alembert-Lachien scalar curvature. And these coefficients A, B, and C are called central charge. So if TUV is 0, the trace of TUV is nothing but twice of T theta theta. Because TUU is because TUV equals 0, we have T theta theta plus T phi phi. But from spherical symmetry, they should be same. So we have twice of T theta theta. Then for the metric, this is the metric we are considering. And so the structure is B, is R squared over 2C, and capital A is again R over 2C. So for this metric, we can calculate F and G. This is Weyl tensor square, can be written like this. And for this behavior, we can easily calculate. This one is 1 over 3C squared. So this is constant. So this dots mean the 1 over R squared corrections. So we assume R is larger than Planck length. So this one is 1 over R squared correction. So and also for the Gauss-Bonnet, we can obtain this formula. And this one is small. This is proportional to 1 over CR squared. So in the trace anomaly, only the C coefficient remains. C coefficient is a coefficient of Weyl squared. So they are small. So we have this equation. T theta theta is T theta. This is twice T theta theta. T theta theta is CW divided by 2. So and sorry, I forgot. Yes, and this is 1 over 3C squared. So CW divided by 2 multiplied by this equal to this. And also from this equation, we can calculate TUU and TVB in terms of T theta theta. So in this way, we can calculate all the components of the energy momentum tensor in this metric. So now we can check the self-consistent equation. So the self-consistent equation, or the semi-classical Einstein equation, is G mu nu equal to 8 pi G multiplied by expectation value of T mu nu. So this is our metric. So from this metric, we can calculate the component of Einstein tensor. And the result is here. And GTT is minus 1 over R squared. And GRR is 1 over R squared. And G theta theta is 1 over 2C. So this is a result of the left-hand side. For this metric, where Einstein tensors are given by this. And we have calculated energy momentum tensor under this metric by using 4-dimensional wire anomaly. So result was this. T theta theta was CW over 6C square, and TU and TBV are written like this, and TUV is 0. So if we compare these terms, I think it's easy to see that, sorry, before that, we have to change this to a diagonal component. So here, so from this diagonal component is this one, from the, from from these two. From these two, we can calculate TTT and TRR. And after a bit calculation, we can show that diagonal TT is minus proportional to 1 over R square, and also diagonal TRR is proportional to 1 over R square, and T theta theta is a constant. So we can compare these three with these three, and so this is 1 over R square, 1 over square, R square, and 1. So again, we have 1 over R square, 1 over R square, and 1. And the overall constant is 1 over 2C and this one. So these three matches if capital C is proportional to this one multiplied by 8 by G. So actually, so if we take capital C in such a way that this equation is satisfied, then the self-consistent equation is satisfied. So in this way, so the argument was the following. First, we make the ansatz, we conjecture that this is a metric. So we made a candidate metric starting from multi-shell model. And then by using wire anomaly, we calculate energy momentum tensor. And actually, this one is satisfied if C is chosen like this. So here we see that C was the strength of the Hawking radiation, and that is proportional to the central charge. And essentially, central charge means the degree of freedom of the field. So the Hawking radiation is proportional to the degree of the freedom of the field. So far we have assumed TUB equals 0, but we can generalize it. So a more general assumption is that we have considered TUB equals 0, but of course this is equivalent to the diagonal TT is equal to minus of diagonal RR. So the energy density is equal to the pressure in the radial direction. So this was what we have assumed. And this assumption comes from the assumption that the energy emitted from each shell simply flows to infinity without being reflected. So with this assumption, we had this equation. So the corresponding to this, the metric satisfies GTT equal minus GRR, which is equivalent to AR equal BR. So here we do not assume it, but keep TTT and TRR independent. But as we have seen there, we can expect that these two are comparable. So we parameterize their ratio as like this. TRR divided by minus TTT is some constant. And we assume that this F varies slowly with R. And in particular, it is natural to expect that F is a constant for conformal matter because of scale invariance. And the assumption that TUB equals 0 corresponds to F equal to 0. So if F equals 0, this is 1. So in this general case, we can again examine the self-consistent Einstein equation. And Oh, sorry, it's already 6:16. So I think I should be brief. So anyway, in this case, we can also solve this one, and in the former case, we set f equal 0, and using that we solve this. And again, using this expression, this assumption, we can solve the equation. And here we have assumed that A and B have power-like behavior in R. And then we have these equations. And from this, we get the generalized result. So again, A and B are proportional to R squared, but we have some correction to them. So this part I already discussed. In this formulation, we need just a field theory. And also, I would like to point out one remarkable point. And this energy momentum tensor is not locally isotropic. As we have discussed, the energy density is proportional to 1 over R squared. And also, the radial pressure is also proportional to 1 over R squared. But the tangential pressure is order 1. So in this sense, tangential pressure is much larger than radial pressure. So the inside of the black hole is far from fluid. So this result is rather surprising, but natural from the construction based on the multi-shell models. So next, I would like to discuss quantum fields inside the black hole. So we have discussed T mu nu by considering wild anomaly, but here we evaluate T mu nu more concretely for free scalar field. And we discuss S waves and Hawking-like radiation and full dynamics, including all partial waves. So in order to discuss Hawking-like radiation, we consider the time evolution of S waves of scalar fields in iconar or two-dimensional approximation in the background geometry. So this is a geometry we are considering. Outside the surface, we have Vijay, and inside the surface, we have this dense metric. And dA du is proportional to capital C divided by AU squared. And here the symbol eta is 1 plus F. Okay. So for simplicity, we can set F equals 0 or eta equal 1. So we have some object with surface of radius capital R, and this R becomes 0 if U is large. So in the Penrose diagram again, so we have our Penrose diagram is the geometry, the topology is the same as the Minkowski space, and we have a small U coordinate here and capital U coordinate here, and we have inside the object we have a Minkowski space. So we have this part is flat, and this is the flat part, and the wave propagates go like this. So this part is in vacuum, in flat space, and then the wave propagates in this dense metric. So as we will see now, the time dependence of the metric create particles. So this is the point. So although we do not have horizon, we still have Hawking-like radiation. This is why I said like. It's not the same as Hawking radiation, but eventually we'll see the same strength of the Hawking radiation. Actually, we have already seen that from this argument, there should be radiation. But here we explicitly evaluate the Hawking-like radiation. So in this background geometry, we consider the time evolution of S waves of scalar fields in iconar approximation. And actually the flux of the particle creation is given by this formula. This is TUU and multiplied by 4 pi r squared. So this is a flux of Hawking radiation. And this can be expressed in terms of Schwarzschild derivative between small u and capital U. But as we have seen, and this Schwarzschild derivative can be written like this using this coordinate. Xi is log d capital U, d small u. Using this coordinate, the Schwarzschild derivative can be written like this. This is first derivative of xi square and second derivative of xi. But this xi is the ratio between capital U and small u. So this is nothing but the square root of this part. So by taking log, xi is half of this. So xi is this. But capital R, this is position of the surface, but this is close to small a. So this is close to this. So we want to take a u derivative of this one. But we know dA du is given by this, by Hawking radiation. So we have a divided by 2c eta multiplied by dA du. And by plugging this, we have this is 1 over eta a. So we know this. And also the second derivative is smaller than this with 1 over r. So this case, this part dominates. So we have square of this. So again, we have Hawking radiation. The radiation is proportional to 1 over a squared. Okay, so this is how we get Hawking radiation without having horizon. And then also we can discuss full dynamics of the field. So we can show that expectation value of T mu nu satisfy the semi-classical Einstein equation. So this time we start from this static metric, and under this metric we consider lower energy state psi for some scalar field phi. And then once we can find the wave function for lower lying state, we can calculate the expectation value of T mu nu. And technically we use dimensional regularization. And then from G, as we have seen, we can calculate Einstein tensor. And by equating these two, we get a self-consistent equation for eta. So in this way, again, we can check the self-consistent Einstein equation satisfied for this metric. And as a result, we have seen the lower energy state. Only in the lower energy state, only S waves are excited that express the collapsing matter and the Hawking radiation. And on the other hand, modes with large angular momenta emerge as bound mode in ground state. So from this, so essentially just S wave can go in and can go out. So the dynamics is controlled by S wave. So the entropy, so information is maintained by these S waves. So essentially we have one-dimensional system. So the entropy is proportional to the radial length of this metric. So, but the important point is this is GRR. So if we take square root, we have R. So if we integrate over R, we have R squared. So this part is proportional to the area A. So in this sense, the entropy is proportional to area. So again, we recover this famous formula. So in the ordinary picture, entropy is around the horizon, but in this picture, entropy is distributed along R, but the total entropy is the same as the area. And also for the modes with large angular momenta, since our modes with large angular momenta create pressure in the tangential direction, we can evaluate the pressure and we see the result is order 1. Order 1 means not 1 over R squared. This is what we wanted. So this means sometimes they claim that 4-dimensional black hole is unstable because we can not have such large pressure. But actually, as we have seen from 4-dimensional wide anomaly, we have large pressure. And also from this explicit calculation, we can show we have large tangential pressure. So I think we should stop around here. I prepared some result that we are doing now, but so I think I should skip this part, and I'll go to the result. So this is a summary. So macroscopic black holes are described by the self-consistent equation or semi-classical Einstein equation. And spherically symmetric solutions are obtained by using the 4-dimensional conformal anomaly. And in this argument, field theory suffices to describe such object. And they look like the conventional black holes from the outside, but their interiors are filled up with matters. And they have no horizon or singularity, and they simply evaporate as ordinary objects. But still we have many questions. So for example, still we don't know the precise matching of the black hole entropy and the number of microstates. As I said, entropy comes from S waves, but so far we didn't have the precise matching. We don't know the overall constant. And also, we can roughly say, we can say that information comes back, but how does the information comes back? We want to know precisely how it happens. And also, the one more serious question is if we consider the conserved quantities like baryon number. So if baryon number is really conserved, so we have to know some mechanism how it comes back. So, and I think we have many questions about this, but I hope our model is rather robust, and we can conclude, we can make some answers to these questions. Okay, so thank you very much.
Yeah, thanks
Thank
for,
you.
yeah. Karen, go ahead, yeah.
So if there are any questions, I mean, I think this would be a good thing. So I actually have a rather naive question. So the initial assumption is that we have an evaporating black hole. And so taking this, we give it a purely geometrical description. That's the starting point. And then we match it with the semi-classical Einstein equations. How do you know that the semi-classical Einstein equations are satisfied throughout this evolution? Like, why do you expect that to be satisfied?
Okay, so one thing I can say is, sorry, I should come back to this one again. And I think, yeah, okay, so as we have seen, the curvature is, if central charge is large,
okay,
the curvature is smaller than 1 over Planck length. So this means the quantum effect for gravity is not so large. So in this sense, if CW is large, curvature is small, and we don't have to consider the quantum fluctuation of gravity. So this means a semi-classical Einstein equation. We treat G mu nu as classical field, but we treat the other fields quantum mechanically.
Okay.
So I think this part, this result.
So these results are valid for the Vaidya case, right?
Pardon me?
This is valid when we're considering the Vaidya setup, like when we're going to a Vaidya sort of analysis of considering just null shells. I just wonder about what would happen if you considered like the true, full-fledged Schwarzschild background with its own potential outside. And I mean, is this, would the analysis be exactly similar, or would we see?
So okay, for a while, okay, we can forget about the multi-shell model. So we can start from this metric.
The original one.
Yeah, so this metric, right?
Okay.
And this metric has, and from this metric, we calculate the Kretschmann. And we know the curvature is not too large. Not too large means proportional to 1 over central charge.
Okay, so it still goes through even in these coordinates.
Yes.
Even in this.
Yeah.
So in some sense, Kawai-san, you are assume some particular solution match with the conformal anomaly, while anomaly.
Yes, yeah. So yes, it's true. So this is what. Sorry, I did it too slowly.
Yeah, I think it's very clear to me. Yeah.
Yeah. So here, okay, I skipped this part. So here we consider a general solution to this one. So we have so far we have considered capital A and capital B power-like behavior.
I see.
So within this assumption, we get that solution. Capital A and capital B are proportional to R squared. So, but this equation is really strong. Here we use just a conformal anomaly.
Yeah, but in some sense, these are inside of black hole. In your construction, in some sense, I always think about this more like people usually call this elliptic compact object, right?
Yeah. Very good.
Here you need to have the boundary junction condition.
Yeah, that's right. Yeah. So okay, this equation is always true. Okay, because this is just a conformal anomaly.
Yeah.
But for equation state, we know in the inside of our object, the equation state can be approximated by this. But outside, we don't know.
Yeah.
Because to get this, we use the multi-cell model.
But do you think I'm more concerned about if I believe this conjecture? I think at this moment I tend to believe this give a nice construction. But I wonder if you predict many things which give the same result as the usual black hole, right?
Yeah.
Do you see how we can test by observation data if this is real? Is this really different from the usual black hole or not? For example, if I consider tidal force, do you think they will give different response than the usual?
Okay. So test means probably okay maybe for primordial black hole, we can see how they evaporate, right?
Okay.
Yeah. So if we can make this model precisely, we can see how they evaporate. Right. So for example, by solving the model explicitly, how does the information come back, we can answer. So we have some precise time evolution of these things. And then we can compare with experiments. So in principle, it's doable.
But it's very difficult to observe directly.
Oh yes, yeah.
Primordial black hole information.
Yeah, I agree. But if we have plenty of primordial black holes or remnant of them, maybe we can say something.
Okay. Yeah. So in some sense, it's what protect by the stack of this inertia. Such that in the outside it look like the ordinary black hole, but inside it's completely different, right?
Yes.
Okay. Yeah. Thanks. Yeah.
Thank you.
Yeah, it's a very nice talk. Yeah. Thank you very much. Yeah.
Any other questions? If not, then let's thank Kawai-san for a very nice talk.
Yeah, thank you. Thank you.
Thank you very much.
Yeah. So have a nice weekend. Okay.
Yeah, you too. Yeah.
Okay. Bye-bye.
Bye-bye.